On the night of October 18th, 2017, the Pan-STARRS 1 telescope at Haleakala Observatory sat open on the summit of Maui's dormant volcano, its wide-field camera sweeping a familiar sky. The air at that elevation was cool and clear, and the telescope moved through its programmed sequence of pointings with the patient, unhurried rhythm of a machine that had been doing the same work for years. Nothing in the sky that night announced itself as unusual. The automated detection system processed each new frame against the accumulated catalog of known objects, and finding what it expected to find, filed the images away without any flag or alert. The dome sat open on the mountain. The camera kept recording. The object was already in the data. Robert Warwick came to those images the following morning. His role with the Pan-STARRS survey involved manually reviewing the previous night's data, looking at frames the automated system had cleared, checking by eye for anything the software might have missed. It was careful, methodical work, the kind of work that requires a trained eye and a willingness to spend time with large quantities of ordinary sky. Most of what a survey telescope records is genuinely unremarkable, cataloged asteroids following their known orbits, background stars fixed precisely where the stellar database predicts them, the steady and accountable population of a solar system that has been mapped in substantial detail over many decades. Warwick was looking for something that did not fit. Most mornings, nothing did. On the morning of October 19th, one frame held a point of light that was slightly out of place. It sat against the background of stars, the way any small solar system object might, faint and unremarkable in isolation, but it had moved between successive images at a rate that did not match any cataloged body. It was moving across the sky at a noticeably fast angular velocity, faster than a distant asteroid on a conventional orbit, faster than the automated system's parameters had been tuned to flag. Warwick looked at it carefully. He checked the successive frames. The point of light was real, its motion consistent across images, its position tracing a short arc through the field. What he was looking at was not a processing artifact or a cosmic ray strike on the detector. It was a genuine object moving through the inner solar system at a velocity that was already notable before the orbital calculations were run. The object received a preliminary designation within the standard system used by the Minor Planet Center to track newly identified bodies before their orbits are confirmed. Warwick reported the detection, the supporting measurements were filed, and within days the astronomical community was working to characterize something that had already been in the solar system for weeks without anyone knowing it was there. The Pan-STARRS survey had been running since 2010, designed precisely to catch fast-moving and potentially hazardous objects in the near-Earth environment, and it had done what it was built to do. One astronomer had sat with a morning's worth of image data and found, in the middle of a perfectly ordinary professional task, an object that had never been seen before and could not easily be accounted for by the existing population of solar system bodies. What made the object immediately unusual was not its presence in the sky, but its brightness variation. As observing teams around the world were notified and began directing their own telescopes toward the object's coordinates, the photometric data coming in from multiple instruments told a consistent and striking story. The brightness of the object fluctuated over time, not the gradual dimming and brightening associated with a slowly rotating, elongated asteroid, but a sharp, deep oscillation over a period of hours. The measurements showed peaks and troughs in reflected sunlight, with a ratio of approximately 10:1. At its brightest, the object returned roughly 10 times more light than at its faintest. For most solar system objects, a brightness variation ratio of 2 or 3:1 is enough to suggest an elongated shape. A ratio of 10 to 1 was something different, something much more extreme. The light curve, the graph produced by plotting those brightness measurements over time, showed a pattern that no known solar system body had ever produced. Each peak in brightness corresponded to the object presenting its broadest face toward the sun and toward the telescopes recording it, and each deep trough corresponded to an edge on orientation, a dramatically thinner profile catching and returning far less light. What the shape of that brightness oscillation implied was either an extraordinarily elongated body, something cigar-shaped, far longer than it was wide, or an unusually flat disc-like form, something that was very wide across, but very thin in the perpendicular direction. Either way, the geometry implied by those measurements was unlike anything cataloged in the solar system. Ordinary asteroids tumble and reflect light variably as they rotate, but the range of that variation falls within predictable bounds established over decades of observations. The object detected by Werik on October 19th fell well outside those bounds, and the data was not ambiguous on this point. The 10 to 1 brightness ratio was simply there in the measurements, patient and precise, waiting for an explanation. The orbital calculations arrived quickly, and they contained a second striking result. The object's trajectory through the inner solar system described a hyperbola, a path that would bring it close to the sun and then carry it away, never to return, on a curve that no bound solar system body could produce. A body gravitationally bound to the sun travels on an elliptical orbit, closing back on itself over time. A hyperbolic orbit does not close. It comes in from one direction, curves around the sun at closest approach, and departs in a different direction, continuing outward indefinitely. The critical number in characterizing such a path is the orbital eccentricity. A value of exactly 1 describes a parabolic orbit, the boundary case of an object just barely unbound. The eccentricity measured for this object was approximately 1, 2. It was not a boundary case. It was clearly, definitively, unhesitatingly hyperbolic, and the excess was large enough that measurement uncertainties could not explain it away. The incoming direction of travel, traced backward through the orbit to its origin, pointed toward a region of sky near the constellation Lyra. The object had not originated in the Oort cloud, the vast reservoir of distant cometary bodies that encircles the solar system at its outer edge. It had not been scattered from the Kuiper belt or perturbed inward from some distant region of the sun's gravitational influence. Its velocity at the boundary of the solar system, what astronomers call its hyperbolic excess velocity, the speed it retained after the sun's gravity had taken its full effect, was approximately 26 kilometers per second. That speed, combined with the eccentricity and the incoming direction, established without ambiguity that the object had originated outside the solar system entirely. It was interstellar. It had traveled from somewhere else through the vast darkness between stars and had passed through the planetary system of the sun on a trajectory shaped by no local gravity and no local origin. The solar system's known catalog of small bodies ran to hundreds of thousands of objects, and none of them had ever carried a designation like this. The object was given the formal designation 1I/2017 U1, the numeral 1, the letter I standing for interstellar, the year and the alphanumeric code of discovery. The letter I had never been used in that designation system before. The object was the first of its kind in the formal record, and the record gave it a category that nothing else yet occupied. The naming of astronomical objects is a process that carries its own weight of tradition and care. For objects discovered in or passing through the Hawaiian sky, the Pan-STARRS team works with Hawaiian cultural practitioners and language experts to identify names that are both meaningful in the language and appropriate to the nature of the discovery. For this object, the name chosen was Oumuamua, a word in the Hawaiian language that carries layered meanings associated with the idea of a scout or a messenger arriving first from a distant place, something that goes ahead, that reaches a location before others do, that comes from far away and arrives before the main body follows. The word is not a simple direct translation of any single English concept. Its meaning is bound up in the context of navigation and exploration and the act of being first to arrive at a place that was previously far. For something that had traveled for an unknown but certainly immense duration through interstellar space before arriving at the solar system, the name held a quiet and specific rightness. The International Astronomical Union formally adopted it. In the official literature, in the scientific papers, in the databases and the observatory reports, the object became Oumuamua, Hadudala, the name of the volcano, and the observatory on its summit carries its own meaning in Hawaiian, often translated as the House of the Sun. The observatory there sits at roughly 3,000 meters above sea level, above a significant fraction of the atmosphere's water vapor, in conditions that make for consistently excellent observing on clear nights. The Pan-STARRS 1 telescope, operating on that summit, uses a 8-meter mirror and an extremely large mosaic detector array, capable of imaging a 7-square-degree patch of sky in a single exposure and surveying the entire accessible sky in a matter of days. It was built with the specific goal of finding fast-moving, potentially hazardous objects, near-Earth asteroids and comets that might represent a risk to the planet. And it is this capability, this wide-field and time-domain approach to surveying the sky, that made it the instrument that ultimately caught the first interstellar visitor in the record. Not a large targeted telescope, not a space observatory, but a wide-field survey camera on a Hawaiian mountain, sweeping patiently and recording everything, letting a careful human eye work through the previous night's data the following morning. There is something particular about the sequence of that discovery, the automated system processing the images and finding nothing to flag, and then one person sitting with the same data and finding the thing the algorithm had not been tuned to notice. The automated detection system was looking for known types of anomalies, objects that fit the profile of objects the survey had been designed to find. Oumuamua's angular velocity was outside the parameters the system was optimized for. Werek's review was not constrained by those parameters in the same way. He was looking with trained attention rather than pre-specified criteria, and the difference between those two modes of looking was the difference between the object being found and the object passing through the solar system entirely unrecorded. The data was the same. The result was different. It is the kind of detail that once noticed does not easily leave the mind. By the time the object had been formally designated and named, by the time the orbital calculations had been confirmed, and the hyperbolic nature of the trajectory was established beyond any procedural doubt, the community of astronomers working to characterize Oumuamua had come up against a constraint that nothing about the discovery itself could resolve. The object had reached its closest approach to the Sun, its perihelion, on September 9, 2017. That was more than 5 weeks before Werek found it in the Pan-STARRS data. At perihelion, the object had been inside the orbit of Mercury, closer to the Sun than any planet, moving at its fastest and presenting the most favorable geometry for close observation. By October 19th, when the discovery was made, Oumuamua was already receding, It had already completed the inward leg of its passage and turned outward on its hyperbolic exit path. Every day after the discovery was a day of greater distance and fainter signal, the object moving away at hyperbolic excess velocity, growing dimmer as the inverse square of its increasing distance from both the sun and the earth. The observational window, the period during which Oumuamua was close enough and bright enough for meaningful characterization with the ground-based telescopes available, was approximately 11 days. Major observatories pointed their instruments toward the receding object during that window, and the data they collected during those 11 days would become the entire empirical foundation for everything that followed. Every measurement of its brightness variation, every spectral color index, every astrometric position used in the orbital solution, all of it was gathered within that narrow interval before the object faded beyond the detection threshold of even the most sensitive ground-based systems. The Hubble Space Telescope tracked Oumuamua in late October and into November 2017, extending the astrometric baseline somewhat, but the time for comprehensive physical characterization had closed with the ground-based window. 11 days across a discovery that had already missed the object at its most observable is a very short time to understand something genuinely new. It is long enough to measure the brightness oscillation repeatedly and build a reliable light curve. It is long enough to obtain spectral color measurements. It is long enough to track the position through multiple arcs of the orbit and refine the trajectory with high precision. It is not long enough to resolve ambiguities about the object's physical shape, its composition, its interior structure, or the detailed nature of its tumbling rotation. The instruments and the astronomers directing them worked quickly and carefully within those 11 days, and they extracted from the data everything that the data could yield. What it yielded was consequential and strange, and in several respects without precedent in the record. But it yielded it in 11 days from a single observational campaign with no possibility of follow-up and no prospect of return. In the weeks after Oumuamua's formal designation and naming, there was a period during which the broader astronomical community absorbed what the survey and the rapid follow-up campaign had documented. The first interstellar object confirmed in the formal record, a body that had come from another stellar system, moving through the sun's gravitational field on a hyperbola, tumbling in a way that produced an extraordinary range of reflected brightness, lacking the spectral characteristics of any familiar solar system body type, and already receding beyond the reach of comprehensive observation. The object was interesting in the specific, grounded way that a genuinely novel data point is interesting when the field that receives it has no established framework into which it fits cleanly. The researchers who had obtained the photometric measurements during those 11 days returned to their data repeatedly in the weeks and months that followed. The light curve was analyzed by multiple teams working from the same underlying observations, each bringing slightly different modeling approaches to the question of what physical shape could produce a 10-to-1 brightness variation, with the periodicity measured during the campaign. The color indices were compared against the spectral properties of known solar system body types and against theoretical predictions for objects with long histories of irradiation in the interstellar medium. The orbital solution was refined as additional astrometric measurements were extracted from archival survey images that had inadvertently captured Oumuamua before it was known to exist. Faint precovery detections that extended the positional record backward by a few days, tightening the constraints on the orbit. All of that subsequent analysis was working from the same fixed and finite dataset, the 11 days of deliberate observation and the scattered archival points recovered before the discovery. There would be no new observations. The object had gone. It was moving at hyperbolic excess velocity through the outer solar system, growing more distant every day, already beyond the orbit of Saturn, before most of the community had fully processed what the discovery represented. The accumulated data from those 11 days was everything that existed: a set of brightness measurements, a set of spectral color indices, a set of astrometric positions, and a set of non-detections, searches for emissions or signatures that were not found, all gathered in a brief and urgent interval by a collection of instruments that had been redirected from their usual work to characterize something unprecedented before it vanished. The dome at Haleakala had been open on the night of October 18th. The camera had recorded the sky in its usual sweep, and Oumuamua had passed through the frame as a faint, fast point of reflected sunlight, already moving outward, already receding from the closest approach that no telescope had watched. One astronomer had sat the next morning with the previous night's data and found it, the designation one eye had been applied to a category that had never existed in the formal record before that day. The name Oumuamua had been formally adopted, carrying the sense of a scout arriving first from far away. In the observational window, the total time the community had to look at it, with instruments capable of measuring its properties, was 11 days. That number, 11, settles with a certain particular quietness when considered against the scale of the journey the object had made to arrive at the solar system at all. Something that had traveled through interstellar space at the speed implied by its hyperbolic excess velocity for a duration measured in millions of years or more, had passed through the most densely surveyed region of the solar system during a period when a single wide-field telescope on a Hawaiian mountain was sweeping the sky on a standard survey cadence. The automated detection system did not flag it. A careful human review found it the following morning. By the time the instruments were pointed and the observations were underway, the object had already been at its closest and was moving away. The window that remained was 11 days. And in those 11 days, the data that came in was strange enough to occupy researchers for years afterward, returning again and again to the same finite set of measurements, working to understand what those measurements implied about something that had passed through once and would not return. The light curve with its 10-to-1 brightness variation remained in the archive. The orbital trajectory, hyperbolic and unambiguous, remained in the record. The designation 1I/2017, 1, the first entry in a category that had not existed before, remained in the formal literature of solar system science. The observational window had closed at 11 days. What had been gathered in those 11 days was all there would ever be, and the object was already far away, moving outward through the darkness at 26 kilometers per second on a path that no gravity in the solar system could bend back toward a second look. The graph arrived before the explanations did. What the Pan-STARRS photometric measurements produced in those first hours of analysis was a line, or rather a series of lines connecting points that rose sharply, fell away to almost nothing, rose again, fell again, in a pattern that covered roughly 10 hours of recorded brightness data and looked unlike any light curve that had been filed in the survey's archive before that morning. Each peak represented the object's broadest face, catching sunlight and returning it toward the telescope. Each deep trough represented the narrowest edge of something rotating through space, turning its thinnest profile toward the sky. The ratio between those two values, between the brightest moment and the dimmest, was approximately 10-to-1. That number, held quietly against the records of every other solar system body ever measured in this way, was its own kind of finding. Most asteroids vary in brightness as they rotate. The variation is usually modest. A typical rocky body tumbling through the inner solar system might brighten and dim by a factor of 2, perhaps 3, across a full rotation cycle, a ratio reflecting the gentle asymmetry of a body that is irregular but not extreme. Some of the most elongated asteroids in the cataloged record push that ratio somewhat higher. What the Pan-STARRS data showed was a ratio so large that a normal elongated shape could not easily account for it. Something about the geometry of the object had to be different. The light was insisting on that, in its careful, impersonal way, without offering any help beyond the numbers themselves. Two possible geometries suggested themselves from that extreme ratio. The first was a shape stretched dramatically along one axis, something long and narrow, a form described in the initial analyses as cigar-like, with a length many times its width, spinning slowly enough that both its longest dimension and its shortest edge came into view across the measurement window. The second possibility, which later modeling would find more physically consistent with the full dataset, was a shape flat rather than elongated, something more like a disc or a slab, thin compared to its other dimensions, presenting a large reflective face on one part of its rotation and an edge so narrow it barely caught any light at all on another. Both shapes were strange. Neither had a convincing parallel in the catalogued record of solar system bodies, where nothing quite that extreme had been described before. The early size estimates built from the cigar-shaped model placed the object at roughly 400 meters in length and 40 meters in width. Those numbers were large enough to carry a certain weight in the imagination, a structure longer than 4 city blocks, narrower than most city streets, tumbling through space at a velocity no solar system body should have. Later work, published in 2019 by Sergei Mishchenko in the journal Nature Astronomy, offered a different picture. Mashchenko's modeling of the full light curve data found better agreement with a flat oblate spheroid, something more like a lens or a thick pancake than a needle. Approximately 115 meters across and only about 9 meters thick, an aspect ratio in that model of something like 13:1, thinner relative to its width than many coins. The numbers changed with the modeling approach, but what they shared was the same insistence on extreme shape and the same silence about how such a shape had come to be. There is a quality specific to reading spectral data, to working with the wavelengths of light reflected from a distant surface, and asking what those wavelengths imply about the chemistry of the material doing the reflecting. The light does not say directly what the surface is made of. It gives a pattern, a signature, a color index, and the task is to compare that pattern against the known signatures of materials whose optical properties have been measured in laboratory conditions, and to find the closest match. For the object now designated 1I/2017 U1, that comparison produced a clear result. The reflected light was reddened, shifted toward the longer wavelengths, in a way that placed the object in a color category shared by some of the most ancient and chemically processed materials in the outer solar system. That reddening is not a random property. Among the populations of small bodies in the outer solar system, the trans-Neptunian objects, the centaurs, the distant cometary nuclei that spend most of their existence far from the sun, a characteristic reddish-brown coloration appears on surfaces that have been exposed to cosmic radiation and ultraviolet light over immense spans of time. The process is slow, accumulative, and irreversible in the sense that it builds layer upon layer over millions or billions of years without being undone. High-energy particles moving through interstellar space collide with the organic and carbon-rich molecules at the object's surface, breaking chemical bonds and allowing them to reform in new configurations, longer chains, more complex structures, a class of altered organic materials known as tholins, named for the Greek word meaning muddy or murky. Tholins are not a specific compound. They are a category, a family of reddish-brown, tarry chemically complex substances that form when simple organic molecules are irradiated over long timescales. The term was coined by the astronomer Carl Sagan and his colleague Bishun Kari to describe the residues they produced in laboratory experiments, simulating the irradiation of methane and nitrogen mixtures, and the color of those residues matched the color observed on the surfaces of distant solar system bodies, with a consistency that suggested a shared history of radiation exposure. The object's coloration placed it in that same family, moderately to strongly reddened, consistent with a surface that had been an open interstellar space for a very long time, absorbing radiation and building chemistry while the solar system was still young, or younger than it is now. It is worth sitting with what that color implies about duration. The reddening process does not happen quickly. Laboratory simulations suggest that the characteristic color depth observed on the most irradiated outer solar system objects requires exposure timescales on the order of millions to billions of years. For a body originating outside the solar system, traveling through the interstellar medium, the radiation environment would have been continuous and largely unavoidable. Cosmic rays arriving from all directions, ultraviolet light from distant stars, the slow chemistry of irradiation proceeding across distances and timescales that do not reduce easily to familiar measures. The color recorded in those spectral measurements was in some sense a record of a journey too long and too old to reconstruct in anything but the broadest outline. The rotation the light curve described was not a simple spin. A body rotating steadily around a single fixed axis produces a predictable, regular light curve, one that repeats cleanly from cycle to cycle, each peak and trough in the same place, the whole pattern as reliable as a clock. The light curve produced by this object was not that. Different observing teams, working with data gathered across the object's brief observational window, produced estimates of the rotation period that ranged from approximately 7.5 to 8.5 hours, a spread that was itself informative. Some analyses suggested the period was not constant across the observation window, that the brightness pattern was shifting in a way consistent with a body not rotating around a single axis, but tumbling in what astronomers call a state of excited non-principal axis rotation. In that state, the body's rotation is more complex than a single spin. The angular momentum, instead of being aligned with one axis, is distributed across multiple axes at once, producing a wobbling, rolling motion whose brightness pattern changes in ways that are difficult to reduce to a simple periodic function. The technical term for the simplest form of this is precession, a slow wobble of the spin axis around the angular momentum vector, but the more disordered versions of this state, where the wobble itself is not regular, can produce light curves that appear almost chaotic to a casual inspection. What this told researchers about the object's history was indirect, but suggestive. Non-principal axis rotation of this kind is typically induced by a collision or a perturbation, some event that distributed momentum across axes and set the body tumbling in a way it has not yet recovered from. Whether that event was recent or ancient, on what scale, and in what setting, the data could not say. There was a detail in the light curve that several research teams noted with particular interest. In some of the analyses, the brightness variation appeared to include secondary peaks within a single rotation cycle, additional brightening events that suggested the shape of the object was not symmetrical in a simple way. A perfectly smooth disk or a perfectly uniform cigar would produce a light curve with 2 peaks per rotation, one for each time the broader face pointed toward the observer. Secondary peaks suggest irregularity, a surface that is not uniform, faces that reflect different amounts of light, a geometry more complex than the idealized models. The data were not good enough, given the object's distance and rate of recession, to resolve those details with confidence. The secondary peaks were noted. They were not explained. The Sun, on the 9th of September 2017, was very close. Not close in any cosmic sense. No gravitational drama was involved. No heating extreme enough to alter the bulk composition of a large rocky body. But close in the specific sense that matters for sublimation. The object passed within 255 astronomical units of the Sun at perihelion, inside the orbital radius of Mercury, exposed to solar radiation at a flux several times greater than what Earth receives. For an icy body, a comet, a carbonaceous asteroid with volatile-rich material near its surface, any object carrying frozen water or carbon monoxide or carbon dioxide in quantities accessible to solar heating, that proximity would have produced a detectable response. A comet at that distance from the Sun is not subtle. The sublimating gas and dust released by solar heating forms a coma, a diffuse glowing cloud surrounding the nucleus that can expand to hundreds of thousands of kilometers in diameter, larger than some planets, luminous enough to be detectable at considerable distances. A comet at that distance also produces a tail, or often 2 tails, one made of dust and one of ionized gas, each pointing in a different direction from the nucleus as the solar wind and radiation pressure push their constituent particles along separate paths. These features are the most reliable signatures of an active cometary body, and they are not difficult to detect. Observatories across the world monitor for them routinely. What multiple observing teams found when they looked at the object during and after its solar approach was nothing. No coma surrounded the nucleus in any optical image from any telescope that turned toward it. The region of sky around the object, examined in image after image taken across the brief observational window, showed the same clean background of stars visible everywhere else in the field. No diffuse brightening, no gentle luminescence of expanding gas, no cloud of dusty particles catching sunlight in the way that cometary material does when it is freshly released from a heated surface. The space around the nucleus was empty in the way that space around an inert, rocky asteroid is empty. Radio observatories contributed their own form of silence. Several facilities turned their instruments toward the object and searched for the molecular emission lines that outgassing material produces, the characteristic frequencies at which water vapor, carbon monoxide, carbon dioxide, and other volatile compounds radiate energy when they are excited. Those frequencies are known precisely. The instruments were sensitive. The direction was correct. What they found was background noise at the detection limit, flat and uninterrupted, in the frequency ranges where an active cometary body, at that distance, should have been producing a signal. The silence was informative in the way that negative results often are, not by confirming a hypothesis, but by constraining the range of possible explanations. An object this close to the Sun, showing no outgassing signature, was either genuinely lacking in volatile material of any kind, or was possessed of something that was suppressing any volatiles it might contain from reaching the surface and sublimating into space. One proposed explanation for that suppression rested on the same reddened surface that the spectral measurements had described. The irradiation mantle, the thick layer of processed organic material built up over potentially billions of years of cosmic ray exposure, could serve a physical function beyond its optical signature. A dense tar-like crust of tholins and other irradiation products, meters or tens of meters thick, might effectively seal the surface of the object against the solar heat that would otherwise drive volatile material upward through pores and cracks. The crust would absorb the heat, radiate most of it away, and prevent the thermal wave from penetrating to whatever volatile-rich material might be preserved beneath. This proposal was physically plausible. The irradiation mantles observed on objects in the outer solar system have measurable insulating properties, and their thickness on the most heavily processed objects could in principle be sufficient to suppress sublimation even at relatively small heliocentric distances. The thickness of the crust would depend on the object's irradiation history, how long it had been in space, how intense the radiation environment had been, what the starting composition of the surface material was. For an object traveling through interstellar space for billions of years, the crust could be thick enough to suppress sublimation at distances far smaller than 0 to 55 astronomical units. The proposal fit the data. It did not resolve it. What sat beneath the surface in that model was simply not accessible to the instruments that had observed the object. Volatile material, ices of various kinds, perhaps water, perhaps carbon dioxide, perhaps something less familiar, might be preserved in the interior, sealed away from solar heat by the processed mantle above, unchanged since some earlier era in the object's history. The non-detection of outgassing did not mean the interior was empty. It meant the surface was quiet. Those two things are not the same, and the difference between them was not something the available data could bridge. The albedo measurements placed the surface in a category consistent with other dark solar system objects. The geometric albedo, the fraction of incoming sunlight that the surface returned toward an observer, was estimated at between approximately 0, 1, and 0.2, a range corresponding to a surface that absorbed most of the light falling on it and reflected only a modest portion back. Dark carbonaceous asteroids and the nuclei of comets tend to fall in this range, or even below it. The nuclei of some short-period comets have albedos as low as 0, 0.2, or 0.3, surfaces so dark that they approach the optical properties of carbon black. At 0.1 to 0.2, the object was somewhat brighter than the darkest cometary nuclei, but still firmly within the range of objects whose surfaces are dominated by dark organic materials. That darkness is easy to describe and difficult to fully imagine. A surface with an albedo of 0. One is returning only 1 photon in 10 that falls on it. The remaining 9 are absorbed, converted to heat, radiated away. In sunlight, such a surface would appear to a nearby observer as a deep matte black, without the reflective gloss of lighter materials, without any brightness that would stand out against the darkness of space behind it. The object would have been invisible to any observer not actively searching for it with a sensitive instrument. It was visible at all only because of the extraordinary light-gathering capability of the Pan-STARRS survey camera and the particular quality of attention that survey work requires. Patient, repetitive, alert to small deviations from the expected background. The irradiation-darkened surface and the non-detection of outgassing were not entirely independent observations. They were consistent with each other in the way that different measurements of the same physical reality tend to be consistent, pointing toward the same broad picture without fully resolving it. A surface built over billions of years of radiation exposure would be dark. A surface thick enough to suppress sublimation would be sealed. A body sealed and darkened in this way would pass close to the sun and return nothing to the telescopes watching it. No coma, no tail, no molecular emission signal, presenting only its rotation, its color, and the sharp brightness variation of an extreme shape against the background stars. That picture was coherent. It described a physically possible object, and it left open the question of what that object actually was, where it had formed, and what history had produced its particular combination of properties. Some researchers noted that the combination of extreme shape and suppressed outgassing was difficult to account for simultaneously within any single straightforward model. The most elongated or flat natural bodies in the solar system, the asteroids and cometary nuclei, whose shapes are known from imaging or light curve analysis, do not typically achieve aspect ratios of 10 to 1 or higher through any well-understood formation process. Accretion, collision, and tidal disruption can produce irregular shapes, but the physics of those processes tends to limit the degree of elongation or flattening that results. An aspect ratio of 10 or 13 to 1 requires something more extreme, either a very specific collision geometry, a very specific tidal disruption event, or some process not well represented in the catalog of known solar system formation mechanisms. This observation was not a conclusion, it was a constraint, one more parameter added to the growing set of properties that any eventual explanation would have to account for. The shape was unusual, the coloration was consistent with immense age, the rotation was tumbling and complex. The passage through the inner solar system had produced no outgassing signature. The albedo was low and consistent with a processed organic surface. Each of these properties, taken individually, had precedent somewhere in the solar system. Their particular combination, in a body arriving from interstellar space on a hyperbolic trajectory, was something that had no direct precedent at all. The light curve was still the sharpest record of what had been observed. It was a graph, a set of measured brightness values plotted against time, the data points connected by a fitted curve, the peaks and troughs spaced across several hours of observation. It did not look dramatic. It looked like what it was, photometric data from a survey telescope, the kind of measurement taken routinely for hundreds of thousands of solar system objects. What made it significant was the amplitude of the variation and the shape of the peaks, and what those features implied about the geometry of something that was already receding before anyone had given it a name. The researchers who first worked with that data were not doing anything unusual in their methods. They were applying standard photometric analysis to a standard kind of observation. The unusual thing was what the standard analysis returned: numbers that did not fit the expected range, a brightness ratio that kept demanding an extreme interpretation, no matter how conservatively it was approached. The data did not change to accommodate more comfortable readings. It simply described, in the flat language of measured values, a shape that had no easy parallel. The reddish surface, built over an immeasurable span of time, absorbed most of the light falling on it. What it did reflect came back in wavelengths shifted toward the red end of the spectrum, carrying the optical signature of chemistry too ancient and too slow to be fully reconstructed from the measurements available. The tumbling rotation distributed that reflected light unevenly across the observational window, brightening and dimming as the object's geometry changed relative to the telescope. And through all of it, through the perihelion passage, through the solar heating, through the brief 11-day window during which instruments across the world could still track its position. The surface gave nothing away. No gas, no dust, no signal at any frequency where outgassing material would have spoken. What the sealed surface held inside it, if it held anything at all, remained on the other side of the silence the instruments had measured. The mantle, in the model that proposed it, was not merely dark. It was thick enough to have been built over geological timescales, thick enough to function as insulation against the sun's warmth, thick enough to keep whatever interior chemistry existed separate from the solar environment entirely. To a telescope, such a surface would look like stone, dense, cold, old, absorbing light, without comment, and returning only a fraction of it in the shifted wavelengths of ancient irradiation chemistry. It would pass through the inner solar system as quietly as something could pass, offering its rotation and its color and nothing further. And beneath that surface, in the model that required an interior to explain the shape the light curve implied, something had been sealed away. What it was, whether ice of some familiar kind, or volatiles of a less familiar composition, or simply the rocky interior of a body that had never been volatile-rich to begin with, the measurements could not say. The sealed surface was the end of what the data could reach. That image, the dark sealed surface moving through space, absorbing nearly all the light that falls on it, returning only the slow color of 1 billion years of irradiation, is a reasonable place to hold what the observations actually established about this object. Not a solution, not an explanation of where it came from, or how its shape came to be, or why its interior, if it had one, was never reached by the solar heat that should have drawn it out. Just a surface, dark and dense and quiet, giving back almost nothing of what the sun poured onto it as it passed through, carrying whatever it carried beneath that sealed and ancient face out into the dark again on the far side of its trajectory, growing smaller in every instrument's field of view until it was gone from all of them entirely. The question of what might be locked inside that surface, held at the distance of genuine scientific uncertainty, rather than any urgency, simply remained. The sequence of numbers that the Michelli team laid out in the spring of 2018 was not, at first glance, the kind of thing that announced itself as strange. A column of measured positions, a column of predicted positions, dates running down one side. The data had been gathered from several of the world's most capable telescopes, instruments at Mauna Kea, at the European Southern Observatory, at the Hubble Space Telescope itself, each contributing a precise coordinate, a moment fixed in the record with the particular care that astrometrists bring to objects that will not pass this way again. The numbers sat in their rows looking like any other set of orbital observations. And then, if a person followed both columns carefully, position by position across the weeks, the two lines began to pull apart. It was a quiet divergence, not dramatic, not the kind of gap a casual eye would catch in a long table of figures, but it was consistent, and it was real, and it was growing. The object had not been where the mathematics said it should be, and the gap between where gravity placed it and where the telescopes found it was, by the time the full data set was assembled, a matter of tens of thousands of kilometers, a number that sounds large because it is, even against the backdrop of the distances involved in solar system dynamics, where tens of thousands of kilometers is still a meaningful displacement from a predicted path. Marco Micheli, an astronomer working with the European Space Agency's Planetary Defense Office, was the lead author of the paper that would formally document this discrepancy. The work had involved pooling astrometric data from multiple independent observatories and running the full battery of known gravitational influences against the measured trajectory. The sun's gravity was there. Every planet in the solar system was accounted for. The general relativistic corrections that orbital mechanics requires at close solar approach were applied. The Yarkovsky effect, the subtle thermal recoil that a rotating, unevenly heated body experiences as it absorbs and re-emits sunlight, was considered. The influence of every catalogued body whose pull was large enough to register was factored in, one by one, until the model was as complete as the current state of celestial mechanics could make it. The residual remained. What the McKelly team published in Nature in June 2018 was that remaining signal, the excess acceleration that survived every attempt to account for it through known physics. The object had experienced a push away from the sun that no gravitational force in the solar system could explain. The push was real, it was measurable, it decreased with distance from the sun in a pattern consistent with a force that grew weaker at the same rate that sunlight itself grew weaker, following what physicists call an inverse square law, diminishing as the square of the distance increased. That pattern was informative. It pointed towards something connected to the sun's light, or the sun's warmth, or both. It narrowed the field of possible explanations without eliminating the uncertainty at the center of any of them. There is a particular quality of attention that arises when a measurement refuses to resolve. The Michelli team had done the work correctly. The data were gathered from multiple independent instruments and checked against each other. The orbital model was the best available. The residual was not a product of measurement error or incomplete data. It had been stress tested against every reasonable objection and had not disappeared. What the team was left with was the clean, undecorated fact of a real physical force acting on a real object, and no consensus on what that force was. That kind of open result has its own specific weight in the scientific record. It does not close. It continues to sit in the literature, available to anyone who returns to work on it. The simplest class of explanation for a solar distance-dependent push is radiation pressure, the force that photons streaming outward from the sun exert on any surface they encounter. Light carries momentum. When photons strike a surface, they transfer a tiny fraction of that momentum to whatever they hit. For objects the size of spacecraft components or dust grains, this force is measurable and routinely accounted for in trajectory calculations. For objects the size of an asteroid or a comet nucleus hundreds of meters across, with masses measured in billions of kilograms, radiation pressure is ordinarily negligible. The surface area of a large body is simply too small relative to its mass for the photon momentum to add up to anything worth measuring against the pull of gravity. For radiation pressure to account for the acceleration the McKelly team had documented, the ratio of surface area to mass would have to be far higher than any known rocky or icy body of comparable dimensions. The calculations ran to a surface mass density of fractions of a gram per square centimeter, a figure that describes an object not much denser per unit of its surface than a sheet of aluminum foil. A body several hundred meters across and yet thin enough and light enough to be moved along by the pressure of sunlight would be a fundamentally different kind of object than any asteroid or comet nucleus that had ever been measured. The density figures from the radiation pressure calculation were not impossible in an absolute sense. They were simply inconsistent with what the physical evidence had so far suggested about the object's dimensions and composition. Cometary outgassing was the other major candidate. When a comet approaches the sun, the heat vaporizes volatile ices from its surface: water, carbon dioxide, carbon monoxide, and those gases escape into space. The escaping gas acts as a kind of low-level thruster, pushing the comet in the direction opposite to the outgassing. This is a known, documented, well-understood phenomenon, and it produces exactly the kind of solar distance-dependent force that the Micheli data described. For an active comet, outgassing is not a strange or exotic explanation. It is the standard mechanism. The cometary outgassing hypothesis was, in that sense, the most conventional available path toward explaining the excess acceleration, the kind of explanation that planetary scientists are accustomed to reaching for when a small body's trajectory shows a non-gravitational component. The difficulty was everything else the data had established about the object's surface and surroundings. In the weeks when the Micheli team's astrometric measurements were recording a definite push, multiple observing teams had been searching carefully for any sign of the gas cloud that outgassing would produce. A comet releasing enough gas to measurably deflect its own trajectory should be releasing a detectable quantity of material. The gas would spread around the nucleus in a coma, a diffuse cloud that would catch and scatter sunlight and appear in optical telescope images as a soft brightness surrounding the object's central point. The searches were carried out. The images were examined. The coma was not there. Darrell Seligman and Gregory Laughlin at Yale University worked carefully within that constraint and arrived at a version of the outgassing hypothesis that was constructed precisely to survive the non-detection problem. Their proposal centered on molecular hydrogen, the simplest and most abundant molecule in the universe. Hydrogen ice, if it formed in the cold of deep interstellar space and remained locked in the interior of a body traveling through the void over cosmic timescales, could in principle sublimate as the body approached a star, releasing hydrogen gas. The crucial feature of hydrogen outgassing in the context of the observational record was that molecular hydrogen is almost entirely invisible to the telescopes that had been turned toward the object. It does not produce the spectral lines that water vapor and carbon dioxide produce. It would not appear in the optical images. It would not register in the radio observations, tuned to detect the molecular emission signatures of the more familiar cometary species. A body outgassing hydrogen could, in principle, be producing a plume entirely invisible to the instrument searching for it, while still generating sufficient thrust to produce the observed trajectory deviation. The hydrogen outgassing hypothesis was an elegant piece of reasoning within the problem it was designed to solve. It offered a mechanism, grounded in known physics, that could produce a measurable non-gravitational force while remaining below the detection threshold of every instrument that had been pointed at the object. It was also, by its nature, difficult to confirm or to rule out. The absence of a detectable signal was entirely consistent with its predictions, which meant that the same observations that could not refute the hypothesis also could not demonstrate it. It was a proposed explanation that fit neatly into the space that the existing data left open without filling that space in any verifiable way. Carbon dioxide was examined as an alternative outgassing candidate on similar grounds. Carbon dioxide ice sublimates at temperatures consistent with solar approach. Carbon dioxide outgassing from a body with a sealed or thermally processed outer mantle might in some circumstances occur at rates below the detection threshold of the instruments available. The same logic that Seligman and Laughlin applied to hydrogen applied here in a modified form. The absence of a detected signature was not, by itself, proof that outgassing was not occurring. It was, rather, a constraint on how much outgassing could be occurring, a ceiling on the rate, derived from the sensitivity limits of the instruments that had searched and found nothing. The searches had been thorough. That is worth holding for a moment. These were not cursory scans by instruments pointed in approximately the right direction. They were dedicated observations using radio observatories specifically configured to detect the molecular emission frequencies of water vapor, carbon monoxide, and carbon dioxide, the outgassing signatures that any cometary body would be expected to produce. The telescopes that had been turned on the object in optical wavelengths were looking for a coma for the diffuse soft brightening that gas and dust would produce around the nucleus, for any sign of material extending beyond the sharp point of light that marked the object's position. Nothing was found above the detection thresholds. The search results were reported with the precision that meaningful non-detections require, not simply as absences, but as upper limits, specific numbers placing a ceiling on how much gas could have been present without registering. What those upper limits constrained was the scale of any outgassing that might be occurring. The amounts required to produce the Michelli team's acceleration were not in all scenarios above the detection thresholds. Some proposed outgassing scenarios were consistent with the non-detections, others were not. The geometry of the problem depended on assumptions about the surface area of the object, its temperature distribution, and the specific volatile species involved. And since the object's precise shape remained inferred from light curve data rather than directly observed, those assumptions carried their own uncertainties. The non-detections were real data. They constrained the space of possible explanations. They did not, by themselves, eliminate the outgassing hypothesis. They narrowed it and left it with a gap at its center that the available observations could not close. It is worth pausing with the inverse square curve itself, the shape of the excess acceleration as a function of distance from the sun. The Michelli team had not merely found that the object was being pushed. They had found that the push followed a specific mathematical form. The curve drawn on a graph of excess acceleration against solar distance was smooth and diminishing in the precise way expected of a force tied to the sun's light or heat, higher when closer, lower when farther, decreasing by the square of the distance as the object moved away. That regularity was itself informative. It suggested that whatever was pushing the object was doing so continuously, not in a burst or an event, and that the mechanism was directly coupled to sunlight in a consistent physical way. A one-time ejection of material would not produce that curve. A single explosive outgassing event would not produce it. The pattern pointed towards something sustained and solar distance dependent, operating steadily across the full arc of the object's observed path. That pattern was, paradoxically, what made the radiation pressure explanation so persistent, even after its density implications had been calculated and found difficult. The shape of the excess acceleration matched radiation pressure almost perfectly, or matched solar-driven outgassing, which follows the same inverse square curve. The data were not ambiguous about the functional form of the force. They were ambiguous about the physical mechanism producing it. A smooth inverse square curve can be produced by photons hitting a surface. It can also be produced by gas sublimating from a surface at a rate determined by the intensity of sunlight. Both mechanisms produce the same mathematical shape. The shape of the curve pointed toward sunlight. It did not by itself point toward either of the candidate mechanisms that rely on sunlight in different ways. Several months after the Michelli paper appeared, other research groups returned to the dataset to test additional explanations. The gravitational influence of hypothetical solar system bodies, the proposed but never directly detected Planet 9, whose existence had been inferred from the clustering of distant trans-Neptunian objects, was examined as a possible source of additional force. The analysis found that no plausible position or mass for a hypothetical distant planet produced a perturbation consistent with the observed trajectory deviation. The geometry was wrong. A distant massive body would produce a pull in a direction inconsistent with the observed acceleration, and the magnitude would not match. Planet 9, whatever its status as a real object, was not the explanation for this anomaly. Close flybys of known or catalogued asteroids were also examined. If an untracked asteroid had passed very close to the object during its solar approach, its gravitational pull might have produced a brief trajectory alteration that appeared in the astrometric data as an acceleration. The search found no candidate object capable of producing the required perturbation at the required time and distance. The catalog of known solar system bodies was extensive. None of them, singly or in combination, provided an explanation that fit the data. The residual acceleration survived the full accounting. There is a particular phrase that appears in papers dealing with non-gravitational forces on small solar system bodies, an accounting phrase that researchers use when they have worked through the known physical influences systematically. After applying gravitational corrections for every known body, after including relativistic terms, after considering thermal recoil and radiation pressure in their standard forms, the phrase that appears is the residual non-gravitational parameter. It is a technical term for the part of the motion that the standard model does not account for. Every active comet with a well-characterized coma has a non-gravitational parameter, and researchers adjust their orbital models accordingly. The number is expected in those cases. It is explained by the observed outgassing. For this object, the number appeared, as it does for comets. The explanation did not. The radio telescope at the Irem Observatory on the Pico Villeta in Spain was among the instruments turned toward the receding object in the weeks after the Michelli paper appeared. IREM is a millimeter and submillimeter wavelength observatory with receivers tuned to the rotational emission lines of molecular gases, the precise frequencies at which carbon monoxide and other species emit when excited. Pointing it at the region of sky where the object was retreating and integrating over observation time was a careful, systematic act of listening. The instrument was suited for exactly the kind of measurement the outgassing hypothesis required. If carbon monoxide was escaping from the body in quantities sufficient to produce a measurable thrust, the IRAM receivers were capable of detecting it, or of determining that no such emission was present above a specific quantifiable threshold. The output showed a flat baseline. The flat line of background noise where an emission signal would have appeared. The frequency channels tuned to carbon monoxide were quiet. Channels tuned to water vapor were quiet. The integration time was sufficient. The sensitivity was adequate. The signal, if it existed at the level required by some versions of the outgassing hypothesis, would have appeared. It did not appear. The non-detection was filed in the record with the care that negative results deserve, precise about the threshold, precise about the integration time, precise about the wavelengths covered, so that future researchers working within the constraints of the existing data set would know exactly how deeply the silence had been measured. That silence accumulated across multiple instruments. Water vapor searched for in optical spectra. Carbon dioxide searched for in infrared. Carbon monoxide searched for in radio. The coma searched for in every deep image. The dust tail, the trailing diffuse brightness that sunlight reflected from ejected particles would produce, searched for in wide field images. All of them returned the same result, recorded in the data tables of multiple papers as upper limits rather than detections, each one specifying how loud the silence had been measured to be. Together, the non-detections described a boundary around the outgassing hypothesis, a set of constraints that some versions of the hypothesis could survive and others could not. The molecular hydrogen scenario survived them. The standard cometary outgassing scenarios did not, at least not at the rates that a straightforward application of the thrust calculation required. The specific difficulty at the center of the hydrogen outgassing proposal was that molecular hydrogen ice is not known to exist in any solar system body. Water ice, carbon dioxide ice, carbon monoxide ice, these are established components of comets and Kuiper Belt objects, detected spectroscopically and incorporated into models of solar system formation. Hydrogen ice requires temperatures close to absolute zero to remain stable, temperatures found in the deepest regions of interstellar space, in molecular clouds where stars have not yet formed. An object that had spent billions of years in the cold between the stars might in principle have incorporated hydrogen ice during its formation, but no cometary body detected in the solar system had been found to carry it. Proposing hydrogen ice as the outgassing agent required proposing a composition that had no precedent in the observed solar system inventory, a necessary step within the logic of the hypothesis, but also the point where the argument reached beyond confirmed data and into material that had not yet been independently established. These were not criticisms leveled carelessly. Seligman and Laughlin had worked through the physics with care and published a serious paper that engaged seriously with the constraints. The response from the broader research community was similarly careful, detailed examination of the proposal's implications, tests of its predictions against available data, identification of the specific evidentiary gaps that remained. This was scientific argument conducted in the published record by named researchers in the specific technical language of the field. The disagreements were real and the uncertainties were genuine, and both were documented in a way that made them available to subsequent researchers. The question had not been answered. It had been more precisely described. The McKelly paper itself was careful about its own conclusions. Its authors had established that the non-gravitational acceleration was real and that gravitational explanations did not account for it. They proposed outgassing as the most natural explanation and noted that radiation pressure on a very low-density body was an alternative. They did not claim to have settled the question. The paper's contribution was not a resolution. It was a precise documentation of the problem, specific numbers, specific constraints, specific residuals that place the anomaly into the scientific record in a form that future researchers could work with. That is, in some respects, a more durable kind of scientific work than a premature answer would have been. The record of what was found, measured precisely, persists independently of whatever explanation eventually proves adequate. The trajectory diagram that came out of the Michelli team's analysis showed two lines. The predicted gravitational path was one, the arc that all the known forces in the solar system produced when applied to the starting position and velocity of an object entering the inner solar system from the direction of Lyra. The measured positions were the other, each telescope observation adding a point to the observed track, the coordinates logged with the precision that modern astrometry achieves. The two lines ran close together for much of the early approach. Then, as the object passed perihelion and began moving outward again, the gap became visible. Not dramatic, not an abrupt divergence. A slow, steady, accumulating separation, the actual positions drifting centimeter by centimeter, kilometer by kilometer, tens of thousands of kilometers by the time the final observations were possible, away from the line that gravity drew. That gap was, in its quiet way, one of the most precisely characterized unsolved problems in the history of interstellar object science. Not the largest anomaly anyone had ever documented, not the most disruptive finding in the literature, but a finding that had survived every reasonable attempt to explain it away, that was consistent across multiple independent data sets, and that pointed toward a physical process acting on this object whose nature the available data had not been able to establish. The gap between the two lines on the trajectory diagram was real, measured, documented, and open. It sat in the published record with the specific weight of things that have been carefully looked at and not yet understood. The listening that radio observatories had done was in its way as informative as the measurements the Michelli team had made. Both were precise, both were systematic, both had found what they found and not found what they had looked for. The Michelli team found a discrepancy where the data should have followed the model. The radio observatories found a silence where the data, if some explanations were correct, should have contained a signal. Together, the two results described the shape of the problem with a clarity that neither data set alone could have provided. Something had pushed this object. Nothing that the instruments could detect had done the pushing. Those two facts, held together, described the edges of the open question with more precision than any available hypothesis had yet been able to fill. The radio output file from ERM still exists in the observatory's data archive. The flat baseline is still there, the quiet channels tuned to carbon monoxide frequency, the integration time recorded, the observation date logged, the sensitivity threshold specified. It is a record of careful listening that heard nothing where it was hoping to hear something and reported the absence with the same precision that a detection would have required. The silence is not incomplete data, it is data. It describes the ceiling below which any outgassing, if it was occurring, had to have been operating. It places a specific quantified constraint on the space where an explanation for the non-gravitational acceleration might still be found. That constraint remains active. The archived measurement is still available to any researcher who wants to work within it. It has not been superseded by a detection because no detection has been made. It has not been rendered obsolete by the discovery of the answer because the answer has not been found. It sits in the record the way all the other measurements from those weeks in late 2017 and early 2018 sit in the record, available, specific, and open to the question that the data surrounding them have described with great precision and not yet resolved. The radio dish listened carefully. The output was flat, and what had pushed this object through its path remains, in the published literature and the archived datasets, a question that was held up to careful instruments and found still unanswered. In November 2018, a paper appeared in the Astrophysical Journal Letters under a title that ended with a question mark. The authors were Avi Loeb, chair of the astronomy department at Harvard University, and Shmuel Bialy, a postdoctoral researcher working in Loeb's group. The paper's title asked whether solar radiation pressure could explain the peculiar acceleration that had been observed in the object's trajectory. It was a peer-reviewed document, formatted in the standard way, carrying the standard apparatus of citations and equations and author affiliations. What made it different from the thousands of other papers published in that journal that year was a single explicit passage in which the authors stated, in the measured language of academic science, that among the possible explanations for what had been observed was the possibility that the object was not natural at all, that it was, instead, an artifact of technology from beyond the solar system. The paper did not assert this. It asked whether the possibility should be considered. That distinction between asserting and asking would become one of the central points of contention in the scientific disagreement that followed. For Loeb, the asking was the entire point. For a significant number of his colleagues, what the paper asked and how it asked it raised questions not just about a particular interstellar object, but about the standards by which unusual hypotheses ought to be admitted into formal scientific discussion. The argument that opened that November, framed initially as a narrow dispute about astrometric data from a single fast-moving object, widened steadily over the months and years that followed into something considerably broader, a debate about scientific culture, about the tolerance for heterodox ideas inside major research institutions, and about what it means to follow evidence responsibly when the evidence is genuinely strange. The specific calculation at the center of the paper was precise. Loeb and Bialy worked from the measured acceleration anomaly and asked what physical object, if pushed by the pressure of sunlight alone, could follow the trajectory that had been recorded. A reflective sheet, they determined, would need to be extraordinarily thin relative to its surface area. The figures they arrived at placed the required thickness somewhere between approximately 0.3 and 0.9 millimeters, while the object's reflecting surface spanned an area of hundreds of meters across. This yielded a surface mass density in the range of roughly 1 grams per square centimeter, less than a sheet of paper, thinner than a credit card, but spread wide enough across space that the sun's gentle pressure could produce the measured push. The calculation did not prove anything. What it established was a set of physical parameters, and then carefully noted that those parameters fell within the range of what current human engineering could theoretically achieve. A thin solar sail of this kind was not physically impossible. It was not even by the standards of the most advanced human technology in 2018 entirely out of reach. The paper left that observation sitting in the formal scientific record without pressing it further. What Loeb and Bialy were proposing, in the plainest terms available, was that the object might be a light sail, a structure designed to travel through interstellar space, propelled by the radiation pressure of successive stellar systems encountered along the way, either a functional probe, still operating in some sense as it passed through, or a piece of derelict debris, an old sail from a civilization that had built such things and might no longer exist, tumbling through the galaxy long after whatever launched it had gone quiet. The paper did not assign probability to either of these possibilities. It placed them in the record as hypotheses consistent with the measured data and left them there. The response from the scientific community arrived quickly and covered a wide range. Some researchers engaged the paper on its technical merits, working through the calculations and offering specific objections. Others addressed what they characterized as a failure of scientific judgment, the premature introduction of an extraordinary hypothesis before the available natural explanations had been exhausted. One line of criticism that appeared repeatedly was methodological, the argument that science is obligated to work through all possible natural mechanisms first, and that reaching for an artificial origin hypothesis before that process is complete represents a kind of shortcut that, regardless of a paper's formal correctness, distorts the priorities of the field. Loeb's response to this criticism, offered in subsequent interviews and eventually in book form, was that the obligation to prefer natural explanations should not become a prohibition against formally stating what the data, considered honestly, does not exclude. Corinne Baylor-Jones of the Max Planck Institute for Astronomy published work that addressed the artificial origin hypothesis from a different angle. If the object was a probe, or even a sail, sent from another stellar system toward ours, or at least passing through in a way that suggested deliberate direction, then its trajectory should carry some information about where it came from. Baylor Jones and colleagues traced the object's path backward through the galaxy, working with the measured velocity and incoming direction to identify what star systems, if any, the object might plausibly have departed from on a direct path. The analysis covered the object's trajectory over a timescale of millions of years, accounting for the motion of stars through the galaxy across that span. The result was the absence of a compelling candidate. No star system emerged from the analysis that could have served as a clear origin point for an object traveling at the measured velocity along the measured path. There were candidate systems whose trajectories came within a reasonable proximity of the object's reconstructed path, but none that produced the kind of clean match that a directed probe's trajectory might be expected to show. The finding was not an absolute ruling out. The object could have been traveling for far longer than the analysis covered, or could have been deflected along the way, but it placed a substantial evidential burden on any hypothesis requiring an intentional origin, a burden that the available data could not lift. This is the shape of how the disagreement actually sat in the literature. Not a clean argument between those who believed and those who did not, but a technical dispute about what the data established, what it excluded, and what standard of evidence should govern the formal consideration of unusual hypotheses. Loeb argued that the anomalous acceleration, the extreme aspect ratio, the absence of a coma, and the trajectory's departure from gravitational prediction together constituted a set of unusual properties that, taken together and honestly examined, could not be adequately addressed by existing natural explanations. His critics argued that unusual properties in a single poorly observed object, combined with the well-established likelihood that natural mechanisms not yet fully understood could account for them, did not meet the threshold required to formally introduce artificial origin as a serious hypothesis. Both positions were held by named researchers at major institutions and documented in published literature. Neither was resolved by the data available. What followed for Loeb personally was a deepening rather than a retreat. The scientific controversy around the paper had been accompanied by an intensity of public attention that few academic astronomy papers ever attract, and Loeb's response to the criticism he received from colleagues was not to soften or qualify the position, but to examine it further and to argue in increasingly explicit terms that the resistance he encountered reflected something worth examining about the culture of contemporary science. He described what he characterized as a taboo within academic astronomy, an informal but powerful norm against formally investigating the possibility of extraterrestrial technology, a norm maintained not by any formal rule, but by the reputational pressures of a competitive academic environment, in which attaching one's name to an extraordinary claim carries professional risk. Whether this characterization accurately described the situation, or whether it misread legitimate scientific caution as illegitimate social pressure, was itself contested. But Loeb pressed the argument, and in 2021, he acted on it. The Galileo Project was announced in July 2021 as an independent research initiative affiliated with Harvard University and funded by private donors. Its stated aim was the systematic scientific search for evidence of extraterrestrial technological artifacts in near-Earth space and in Earth's atmosphere. Loeb raised millions of dollars in private funding in a relatively short period. The project's planned infrastructure included a network of all-sky telescope systems equipped to record the sky continuously across multiple wavelengths, with automated analysis pipelines designed to flag objects whose properties could not be matched to known natural or human-made phenomena. The ambition behind the design was methodological. Rather than waiting for unusual objects to be noticed by general-purpose surveys and then retroactively investigated, the Galileo project would observe systematically and deliberately, applying to the search for possible technological artifacts the same rigorous instrumentation and data archiving standards that any other scientific survey would use. The first all-sky monitoring station was installed and began collecting data, its cameras pointed permanently upward, its recorders running. The scientific community's response to the Galileo project was again mixed. Some researchers welcomed the application of systematic methodology to a question they regarded as worth asking more carefully. Others maintained their objections to what they characterized as Loeb's tendency to present speculative hypotheses in terms that implied a stronger evidential basis than existed. The project attracted coverage in major newspapers, science publications, and general interest media that went considerably beyond the typical reach of an academic research initiative. Part of this was the subject matter. Part of it was the institutional affiliation. A Harvard professor running a formally constituted research project directed at the question of extraterrestrial technology gave the inquiry a different kind of weight in public conversation than the same question posed by a researcher at a less prominent institution would have carried. Whether that weight was earned by the evidence or whether it reflected the particular status of a particular university in the public imagination was a question that hovered around the project's reception without ever being cleanly answered. In January 2021, several months before the Galileo project's formal announcement, Loeb published a book, Extraterrestrial Tokens, named The First Sign of Intelligent Life Beyond Earth, laid out the argument he had been developing since the November 2018 paper, in language aimed at a general audience, rather than the readers of a scientific journal. The book described the discovery of the interstellar object, the acceleration anomaly, the calculations he and Bialy had published, and the reception those calculations received from the scientific community. It argued that the object's properties, taken together, were more consistent with an artificial origin than with any natural explanation proposed to that point. It also argued at some length about the culture of academic science, the pressures that, in Loeb's view, discouraged researchers from pursuing heterodox hypotheses, and what he characterized as the cost of those pressures to the field's capacity to ask genuinely open questions. The book reached the New York Times bestseller list. It was reviewed in major publications by science journalists, by other astronomers, and by researchers in adjacent fields. The reviews were sharply mixed. Readers outside academic astronomy often found the argument compelling, or at minimum found the question it raised worth taking seriously. Many professional astronomers found the book's characterization of the scientific community's response to the 2018 paper unfair, and its treatment of the hypothesis's evidential basis overstated. Several published detailed objections to specific claims in the book, working through the physics and the observational data, and arguing that the natural explanations were considerably more plausible than Loeb's presentation suggested. The debate that the book generated in public was louder, more polarized, and considerably less careful than the debate that had preceded in the peer-reviewed literature. That gap between the technical discussion among researchers and the public argument playing out in reviews and media coverage became, for many observers, its own kind of illustration of how difficult these questions were to discuss accurately at scale. The object itself, of course, was long gone by the time any of this played out. It had left the inner solar system well before the first paper documenting its anomalous acceleration was published, and by the time the debate over its nature reached its sharpest intensity in 2021, it was somewhere in the outer reaches of the solar system, beyond the detection threshold of any existing instrument, moving on a trajectory that would carry it away from the sun indefinitely. Everything argued about it was argued from a dataset collected over 11 days in the autumn of 2017. The object did not respond to the controversy it generated. It simply continued along its path, indifferent to whether the researchers watching its receding signal interpreted it as an unusual rock or as something else entirely. What the debate around the artificial origin hypothesis illustrated, held at whatever distance allows its actual shape to be seen clearly, was not primarily a story about extraterrestrial intelligence. It was a story about the epistemology of anomalous data, the question of how science should handle an observation that is genuinely strange and genuinely underexplained when the data is insufficient to distinguish between multiple competing explanations and the available follow-up observations are permanently foreclosed. Loeb's argument was that a hypothesis should not be excluded from formal consideration simply because it is unusual, provided it is consistent with the measured data and is expressed in falsifiable terms. His critics' argument was that consistency with data is necessary, but not sufficient, that the prior probability of a hypothesis matters, and that an extraordinary hypothesis requires extraordinary evidence before it deserves the serious institutional attention that a Harvard professor giving it formal expression inevitably confers on it. Both arguments are recognizable positions within the actual philosophy of science. Neither is obviously wrong. The data available could not adjudicate between them. What the Galileo project represented, in this context, was one possible institutional response to that impasse. Rather than continuing to argue about what the existing data from a single object could or could not establish, the project's approach was to generate new data, systematic, high-quality, continuously collected observations designed specifically to look for what the existing instrument network had not been designed to find. The logic was straightforward. If the hypothesis is worth seriously entertaining, it is worth seriously investigating, and serious investigation requires purpose-built instruments and rigorous methodology rather than the retrospective analysis of data collected for other purposes. Whether the project's data will eventually produce findings that bear on the questions Loeb has raised, or whether it will produce a large and carefully collected data set of entirely natural phenomena, was not answered by the time the project's early operations began. The instruments kept running. The data kept accumulating. The paper that Loeb and Bayali published in November 2018 was not a long document. By the standards of academic astronomy, it was relatively brief, a focused calculation, a specific argument, a clearly stated hypothesis, and the question mark in the title that had given the whole enterprise its careful framing. It appeared in the formal record of science in the way that all peer-reviewed papers do, assigned a journal and a volume and a page range, indexed in the databases where researchers search the literature. A reader looking for it years later would find it the same way they would find a paper on stellar populations or exoplanet atmospheres, by searching a database, clicking a link, reading the abstract. It did not disappear when the controversy quieted. It did not become less accessible as the debate moved on. It remained where it had been placed, in the archive where the scientific literature accumulates, available to anyone who wanted to read it in the same precise form in which it was submitted. The title's question mark was itself a kind of position. It was Loeb's way of saying that what followed was not an assertion, but a formal inquiry, conducted in the appropriate venue, using the appropriate methods, held open at its conclusion in the appropriate way. Whether that framing successfully distinguished the paper from the stronger claims Loeb would later make in public, or whether the question mark itself was a kind of rhetorical shelter for an argument that already had a preferred answer, was something researchers read differently depending on what they brought to it. The question mark remained in the title regardless of how any individual reader interpreted it. There is a particular quality to a scientific controversy that involves a single object observed for a short time and then gone, a quality different from controversies over phenomena that persist and can be re-examined. The ongoing debates about dark matter, or about the interpretation of quantum mechanics, or about the mechanisms of consciousness, are conducted against a background of continuously accumulating data. New experiments can be designed, new observations can be made, theoretical positions can be tested against new evidence as it arrives. The Oumuamua controversy does not have this character. The data set is fixed. The 11 days of photometry and astrometry and spectroscopy collected between October and November 2017 are the complete record. Nothing will be added to them. Every argument made about the object's nature must be made from the same bounded set of numbers, and no new observation of the object itself will arrive to tip the balance in any direction. The argument proceeds in a space that is permanently finite. This is not unique to arguments about unusual objects. Many of the most interesting questions in science are conducted over fixed or nearly fixed data sets. Questions about the early universe, about extinct species, about geological events in the deep past. Researchers develop skill at working carefully within those constraints, at being clear about what the data can and cannot establish, at resisting the pull toward conclusions that feel satisfying but exceed what the measurements actually support. The Oumuamua dataset is, in this sense, a test case for that kind of discipline. It asks of anyone working with it, what can you honestly say, and what are you reaching for because you want it to be true? Loeb's answer to that question has been consistent. The object had properties that no natural explanation proposed to date fully accounts for, and intellectual honesty requires saying so formally and asking what else might explain it. His critic's answer has been equally consistent. The object was observed too briefly and at too great a distance to fully characterize. The natural explanations are plausible, even if imperfect, and the threshold for seriously introducing an artificial origin hypothesis has not been met by the available evidence. The argument between these positions has not moved substantially since the period immediately following the 2018 paper because the data has not moved. What has changed is the institutional landscape around it. The Galileo Project established and operating, the book written and read by many people, the original paper sitting in the archive, having been cited by a steady stream of subsequent work. The first all-sky monitoring station that the Galileo Project installed continued to collect data after its commissioning. The cameras pointed upward, and the recording systems ran, accumulating observations of the sky above their installation site in the careful and continuous way that Loeb had argued the question deserved. What was recorded was a stream of data: meteors, satellites, aircraft, weather phenomena, cosmic ray detections, and the ordinary background of astronomical sources cycling overhead. The analysis pipeline sorted through the stream, flagging candidates and discarding obvious identifications, working through the data in the way that any automated astronomical survey works through its output. Most of what the cameras saw was familiar. The project continued collecting. The formal scientific record now contains Loeb and Bialy's paper, Baylor Jones's trajectory analysis, the responses and counter-responses published in the years that followed, the Galileo Project's methodology papers, and a growing body of work on interstellar objects more broadly. It's much of it produced in anticipation of future detections rather than in direct response to the single object that started the conversation. A researcher wanting to understand the current state of the debate would read this literature and find at its center the same unresolved question that was present on the day the 2018 paper appeared. What pushed the object along a trajectory that no gravitational force accounted for, and is the most honest thing to say about that question that it remains genuinely and completely open. The Galileo Project's camera array, pointed at the sky above its installation site, continues to run. The images accumulate in the project's data archive, frame after frame of the sky captured at regular intervals, each one added to the record that the project is building. The particular patch of sky where the interstellar object receded in 2017 is no longer visible in the frames. The object is far beyond the reach of any instrument the project or anyone else has available, but the cameras do not require any particular object to observe. They are designed to watch whatever crosses their field of view, recording it systematically and precisely, storing the data in the form that allows it to be analyzed later. The array sits under the open sky and keeps watching, its recorders running, the images arriving one after another into the archive, where they wait to be examined by whoever comes to look. On the morning of August 30th, 2019, at a small private observatory on the Crimean coast called Margot, an amateur astronomer named Gennady Borisov was reviewing images from the telescope he had built himself. The instrument was not a professional installation. It had no institutional affiliation, no government funding, no team of operators working in shifts around the clock. It was the careful project of one person who had spent years assembling the components and learning the sky well enough to notice when something in it did not belong. That morning, moving through the field of stars at a speed consistent with a hyperbolic trajectory, there was an object Borisov had not seen before, and around it, clearly visible even in those early frames, was a faint soft extension of light, a coma, thin and luminous, spreading outward from the nucleus the way a comet's coma spreads when volatile material begins to sublimate in the warmth of an approaching sun. It was the signature that had been absent from every image of the first interstellar object ever recorded. 2 years earlier, the object designated 1I/2017U, one had passed through the inner solar system without producing anything like it. Telescope after telescope had searched the region around that earlier visitor for exactly this kind of haze, the quiet fog of outgassing material, water vapor or carbon monoxide, or some other volatile compound, warming and expanding into space, and had found nothing. The sky around the first interstellar object had been clean. The object itself had been bare and sealed and dark, tumbling on its way without shedding a visible trace of what it was made of. Borisov's object, designated 2I/Borisov, when the International Astronomical Union confirmed its interstellar origin weeks later, was something else entirely. It was a comet in the familiar sense, with a chemistry recognizable to spectroscopes and a behavior consistent with the icy bodies of the outer solar system. It was, in the language researchers used when describing it, an ordinary visitor by extraordinary means, a body from another star that looked, in its composition and its coma and its spectral fingerprint, more or less like the comets that had always been known. The contrast was not lost on researchers who had spent 2 years trying to account for the first object's peculiarities. 2I/Borisov arrived already trailing its explanation, The coma was there, the water vapor was there, the carbon monoxide was detectable at levels consistent with similar comets in the solar system. Spectroscopic measurements made by multiple independent teams over the weeks following discovery returned results that fit comfortably within the existing framework of cometary science. If the first interstellar object had been strange, the second was familiar in almost every way that mattered. Some researchers began to suggest, carefully, that this reversal of expectation was itself informative, that the first object might be the anomaly rather than the norm, a visitor whose strangeness was its own and not a property of interstellar objects in general. Others held that both objects simply represented the range of what the broader galaxy ejected into the spaces between stars, some icy and familiar, some denser and stranger and harder to read. The second interstellar object remained observable for far longer than the first had, because Borisov discovered it months before its closest approach to the Sun. Astronomers had time to prepare, to schedule observing runs, to coordinate campaigns across multiple instruments and wavelengths. The Hubble Space Telescope observed it. Ground-based facilities on multiple continents tracked it. The data set that accumulated over the following months was of a quality that no one had been able to build for the first visitor, and at the end of that extended observation, the conclusion was consistent. 2I/Borisov was strange in origin and ordinary in nature, a traveler from outside the solar system carrying chemistry that felt like home. It was, in its own way, a reassurance, a demonstration that interstellar objects could be studied, could be understood, could yield their composition to patient instrumentation. It was also, by contrast, a quiet reminder of how little the first object had yielded, and how short the window had been for asking. The first object had been discovered already past perihelion, already moving away, already fading. The effective window for useful observation had been measured not in months, but in days. Researchers working with whatever time remained had done what they could: photometric measurements, astrometric tracking, spectral color analysis, radio searches, and infrared search with the Spitzer Space Telescope, and had produced a dataset that was, given the constraints, genuinely rich. But it was also permanently incomplete. There would be no second opportunity. The first interstellar object had moved beyond the reach of any existing telescope before many of the questions it raised had been fully formed, let alone addressed. The Spitzer Space Telescope's contribution to the record was notable precisely because it came from the instrument's inability to detect what it was looking for. In November and December of 2017, the space-based infrared observatory pointed its detectors at the region of sky where the first interstellar object was by then receding, searching for the thermal emission that any warm solid body of significant size would produce at infrared wavelengths. The object was not detected. That non-detection was not a failure in the ordinary sense. It was a measurement, a precise statement about what was not there, which constrained what the object could be. A team led by David Trilling used the Spitzer non-detection to derive upper bounds on the object's size and reflectivity, revising earlier estimates somewhat downward, and narrowing the range of physically plausible models for the object's dimensions. The result did not resolve the fundamental ambiguity about the object's shape. It did not distinguish between the extremely elongated cigar model and the flat disk model that later analysis had proposed as an alternative, but it added a layer of constraint to a data set that needed all the constraint it could get, and it did so through the honest negative result of an instrument that looked carefully and came back with nothing, which is in science a kind of answer. The non-detection at infrared wavelengths, joined a set of other non-detections that formed a substantial portion of what was known about the first interstellar object. No cometary coma had been detected, no water vapor, no carbon monoxide, no carbon dioxide, no dust tail, no thermal emission above background, no radio signal of any frequency attributable to the object itself. The dataset was in part a record of absences, a careful list of things that would have been expected from a more cooperative object, and that this one had not produced. Those absences were not meaningless. Each one constrained the space of possible explanations, ruled out certain models, and pushed the surviving hypotheses toward increasingly specific predictions. The absence of a detectable coma, combined with the non-gravitational acceleration that observations had documented, was the specific tension at the heart of the scientific disagreement about the object's nature, and it was a tension that the available data could not resolve, because the data had run out before the question had been answered. The question of what the object was made of had attracted hypotheses from multiple directions. In 2021, two planetary scientists at Arizona State University, named Alan Jackson and Stephen Desch, published a paper in the Journal of Geophysical Research that offered one of the more carefully constructed natural explanations for both the object's anomalous acceleration and the absence of a visible coma. Their proposal centered on nitrogen ice, the same material that covers the surface of Pluto's Sputnik Planitia, the vast pale plains imaged by the New Horizons spacecraft in 2015. The argument Jackson and Desch made was specific. When a planetary system is young, the period of heavy bombardment in its early history produces collisions between bodies that can shear away surface material and send fragments into interstellar space. A body made primarily of nitrogen ice, sheared from the surface of a Pluto-like object in another system during such a bombardment, would have the right properties to account for what had been observed. Nitrogen ice sublimates under solar radiation, which could produce the non-gravitational push that the astrometric data had documented. The sublimation of nitrogen is optically faint. The gas it produces would be much harder to detect spectroscopically than water vapor or carbon monoxide. The surface of such a body, eroded by sublimation over a long transit through interstellar space, would become flat and smooth, potentially explaining the unusual aspect ratio that the light curve implied. It was a careful hypothesis. It made specific physical predictions and connected the object's strange properties to a mechanism with precedent in solar system science. It also faced challenges. The rate at which nitrogen ice sublimes in interstellar space over billions of years is difficult to calculate with precision, and the total mass loss such a body would sustain during a journey of that length could, under some estimates, exceed the mass of the object itself, raising questions about whether a nitrogen ice fragment of reasonable initial size could survive the transit at all. Jackson and Desch addressed these concerns in their paper and maintained that plausible initial sizes and transit durations made the scenario viable. Other researchers examined the numbers and arrived at different conclusions. The nitrogen ice hypothesis remained what most natural explanations for the first interstellar object remained: plausible, physically grounded, and observationally unverified. The coexistence of multiple competing explanations, all of them physically possible, none of them observationally confirmed, was a situation that would not be unusual in planetary science if the object in question were accessible for study. Most ambiguous cases in solar system science are eventually resolved by better observations, follow-up missions, refined models, or simply by time. The first interstellar object was not accessible. It was moving away from the solar system at approximately 26 kilometers per second, and by the time the scientific community had assembled the theoretical vocabulary to describe what it was asking, the object was already beyond any instrument's reach. The question of whether a mission could have reached it, or whether one might yet be designed to do so, was not idle. It was an engineering problem that several research groups took seriously enough to analyze in detail. A 2019 study by the Initiative for Interstellar Studies examined what it would take to physically reach the first interstellar object, using technologies that either existed or were under serious development. The mission concept that emerged from that analysis was called Project Lyra. The proposal involved a combination of gravitational assist maneuvers, including a close solar passage known as an Oberth maneuver, a technique that uses the sun gravitational well to amplify the velocity gain from a rocket burn, providing a level of performance that would be impossible to achieve at larger heliocentric distances. Even with this technique applied to the most capable launch vehicles under development, and even with travel times measured in decades, the analysts found that catching the first interstellar object in any useful time frame was beyond current engineering capability. The object was moving too fast, and it had too great a head start. A mission launched in the early 2020s would not reach the object before the early 2050s at the earliest, and the scientific return from a rendezvous at that distance, far from the sun, far from Earth's communication infrastructure, after decades of cruise phase, would depend on technologies not yet built. The study's conclusion was not that such a mission was impossible in principle. It was that the first interstellar object had not waited long enough to be caught. The impossibility of a physical rendezvous returned the scientific community to the only data set it had, those 11 days in late October and early November of 2017, recorded by a collection of ground-based telescopes working quickly under difficult conditions, supplemented by the Spitzer non-detection made 2 months later. That dataset had been analyzed many times by many teams using many methods. It had been published and republished, cited and cross-cited, critiqued and refined. The numbers in it had not changed. Astrometric positions are measured quantities, and the positions recorded in the archived files were the positions that had been recorded. But the interpretations placed on those numbers continued to develop, and the conversation around them showed no sign of having reached a point of rest. Part of what sustained that conversation was the expectation, grounded in observational probability estimates, that the first interstellar object had not been genuinely exceptional. Statistical analyses suggested that the solar system likely hosted, at any given moment, several interstellar objects of comparable size somewhere within its volume, objects that had entered from outside and not yet exited, passing through on hyperbolic trajectories that would eventually carry them back out to interstellar space. The reason the first interstellar object had been the first was not that it was the only one, or even that it was unusually large or bright. It was that the survey capacity required to detect it had only recently become available. The Pan-STARRS Survey Telescope on Halakala had been imaging the sky with the combination of field of view, sensitivity, and cadence required to catch a fast-moving, moderately dim object at a useful distance. Earlier surveys had lacked one or more of those capabilities. The first interstellar object had been detected because the instrument looking for it had finally become powerful enough to find it, not because the object had gone out of its way to be found. That framing pointed toward a future rather than a past. If the detection had been a function of survey capability rather than a rare astronomical event, then better surveys would produce more detection. and among the instruments expected to change the frequency of interstellar object detection was an observatory that had been under construction for years and whose operational readiness was finally arriving. On Cerro Pachon in Chile, the Vera the 100th, Rubin Observatory was completing the preparations for its legacy survey of space and time, a deep, wide, rapid survey of the southern sky that would image the visible universe with a cadence and sensitivity that no previous ground-based survey had matched. The telescope's primary mirror measured 8.4 meters across. Its camera, the largest digital camera ever built for astronomical purposes, covered a field of view of approximately 6 square degrees, meaning that in a single exposure it could image a patch of sky roughly 50 times the area of the full moon. The survey was designed to repeat its coverage of the entire southern sky every few days, building a time domain record that would capture the movement of solar system objects, the variation of stars, the transient brightening of supernovae, and based on predictions published before the telescope achieved first light, between 1 and 10 interstellar objects per year. 1 to 10 per year. The figure came from models of the interstellar object population density built on the detection of the first 2 confirmed visitors, and refined by statistical inference about what the underlying population must look like to produce those detections at the survey rates that existed at the time. The range was wide because the underlying population was poorly constrained. 1 detection and 1 confirming detection were not enough to draw a precise curve. But even the lower bound of the estimate implied that the first interstellar object would not remain the only well-documented case for long. Within a few years of the Vera the 100th, Rubin Observatory reaching full operational status, the catalog of known interstellar objects could grow from 2 to something in the range of 5, 10, or more, and each new detection, if it came early enough in the object's solar passage, would arrive with a longer observational window, enough time for spectroscopic characterization, for detailed astrometric tracking, for coordinated campaigns across multiple telescopes, for the kind of patient evidence gathering that the compressed window of the first visitor had never allowed. The prospect of better data had a specific relevance to the questions that the first interstellar object had left open. If outgassing was responsible for the non-gravitational acceleration, then a future interstellar object exhibiting similar acceleration should also produce detectable outgassing products, water vapor, molecular hydrogen, carbon monoxide, or whatever species the sublimating material was composed of. A robust detection of a volatile species in an object showing non-gravitational acceleration would be a strong confirmation of the outgassing hypothesis as a general mechanism. A robust non-detection in such an object at sensitivities better than those available in 2017 would constrain the hypothesis further or challenge it more directly. Either outcome would say something useful about the first object by analogy, even without a follow-up mission to the object itself. The possibility of such analogical reasoning, testing hypotheses developed for one object by applying them to subsequent objects, was part of what gave the ongoing scientific conversation about the first interstellar object its particular character. The conversation was not closed. It had a future in it. The questions that had been raised in 2017 and 2018 were still formally open, still being examined in published literature, still being carried forward by researchers who had no expectation of a simple resolution. The scientific community's relationship to those questions was not the relationship of people waiting for a verdict. It was more like the relationship of people who had been handed a problem they found genuinely interesting and who had gone back to work on it and who expected to be working on it for some time to come. The archive from those 11 days held 11 days. It was a finite thing. The data files that stored it resided on servers at the University of Hawaii and at institutions affiliated with the observing teams that had contributed to the campaign: the European Space Agency, the Hubble Space Telescope's Science Operations Center, the various ground-based facilities that had tracked the object across the sky as it receded. The photometric measurements were there. The astrometric positions were there. The color indices, the brightness ratios, the upper bounds derived from non-detections, all of it sat in the archive in the same state it had occupied since the observations were made, unchanged by the passage of time, available to any researcher with the credentials to access it. What changed over time was not the data, but the tools brought to bear on it. New modeling techniques, new software for orbital integration, new theoretical frameworks developed in the course of studying other objects in other contexts. All of it could be applied to the archived measurements, extracting interpretations or constraints that had not been extractable when the data was first acquired. A paper published years after the observing campaign could legitimately derive new conclusions from old measurements, not because the measurements had changed, but because the analysis had. This was a routine feature of data-driven science, and it meant that the archive was not merely a record of what had been seen. It was a resource that remained in active use, being worked on by researchers who were not done with it. The tumbling body that had moved through the inner solar system in September and October and November of 2017 was, by any measure, gone. Its distance from the sun by the early years of the following decade was measured in astronomical units, large enough that no existing or planned telescope could have detected it. It was moving in the direction of the constellation Pegasus, continuing the hyperbolic trajectory that had carried it inward from the direction of Lyra, and would now carry it outward again, beyond the heliopause, into the interstellar medium from which it had arrived. The journey it was making was immeasurably long. The solar system it had passed through was a small episode in that journey, a brief period of warmth and light and gravitational perturbation, before the cold and the dark of interstellar space resumed again. Whatever it was, it had not stopped. It had passed through and continued, and the passage was over. What remained was the record of the passage and the community of people who found the record, in its incompleteness and its persistent open questions, genuinely worth attending to. The nitrogen ice hypothesis sat in the published literature alongside the outgassing hypothesis and the radiation pressure calculations and the spectral color analysis and the Spitzer non-detection and the astrometric data showing the positional discrepancy and the orbital solution tracing the incoming path back toward Lyra. They sat together in a body of literature that had grown considerably since the first circular announcing the object's discovery was filed in October of 2017, and that had not finished growing. Researchers continued to return to the questions the dataset posed, not because a resolution was imminent, but because the questions were the kind that rewarded continued attention, the kind that did not become less interesting the longer they went unanswered. The second interstellar object, with its familiar coma and its cooperative chemistry, had done the useful work of showing that interstellar visitors could be ordinary. The first had done the different, and perhaps more lasting work of showing that they could be strange in ways that existing frameworks did not easily accommodate. The two objects taken together suggested that the gallery of what passed through on its way from somewhere else was not uniform. There was variety in it. There were objects that behaved as expected, and objects that did not, and the task of understanding the difference was the same task it had always been in planetary science: accumulate more examples, test more hypotheses, refine the models by which the examples are understood, and hold the current state of understanding at the right degree of looseness, confident where the evidence is strong, open where it is thin, honest about the boundary between the two. That boundary ran through almost everything known about the first interstellar object. The measurements were real, the orbital solution was secure. The color, the rotation, the aspect ratio inferred from the light curve, the non-gravitational acceleration, all of those were observations in the robust sense, reproducible quantities derived from careful instrumental work by multiple independent teams. The interpretation of what those observations implied was another matter, and it was there, at the interpretation, that the boundary between established and open ran most clearly. The object had been described, it had not been explained. The description was stable, and the explanation was not, and researchers working in the field regarded this as an accurate characterization of the situation, rather than a temporary embarrassment, soon to be resolved. The sky over Cerro Pachon on a clear southern night is very dark. The Atacama Desert's altitude and aridity have made it one of the most transparent observing environments on Earth, and the observatory on that particular summit was designed to take full advantage of both. On nights when the survey is running, the 4-meter mirror sweeps the southern sky in a pattern calculated to maximize the chance of catching something that moved since the last observation, something that does not sit still against the background stars, something with a motion that distinguishes it from the vast fixed field of more distant objects. The camera records everything in each field: the faint galaxies, the variable stars, the asteroids, the near-Earth objects, the comets, and on some fraction of those nights, something moving on a curve that does not close, something whose trajectory, when the orbital solution is computed, turns out to be hyperbolic, something from outside. The first time the Rubin Observatory detects an interstellar object, and based on published predictions, that detection may come within its first years of full survey operation. The announcement will look something like the one filed in October of 2017. A circular will be distributed, a designation will be assigned. Researchers around the world will point their telescopes at the listed coordinates. The difference will be the timeline. If the object is detected before perihelion, while it is still approaching its closest point to the sun, and therefore still brightening and drawing nearer, the window for observation will be measured, not in 11 days, but in weeks, possibly months. The spectroscopes will have time to work. The astrometric data set will be large enough to determine the non-gravitational acceleration, or its absence, with a precision that the first data set could not achieve. The questions that were asked too late, or answered only in their negative form, will have a second chance of being asked in time. That prospect, the second chance, is not a certainty. The next interstellar object may pass through in a geometry that limits observation despite the improved survey. It may turn out to be unremarkable, a familiar comet with familiar chemistry that confirms the second object's suggestion that the strange one was the exception. It may turn out to be stranger still. The range of what the galaxy sends through on these long, slow circuits between stars is not yet characterized well enough to say.